All right, we'll get it started. The first talk of the session is going to be given by Felix from Technical University of Munich, and we'll just go ahead.
All right, thanks. Okay, hello everyone. So this survey ended up on my Twitter quite recently, and it nicely describes the problem I want to address in this talk. So it says, I'm a programmer looking for a solution on Stack Overflow to paste into my project. So as you can see, it received a lot of love from the community. Lots of likes and lots of retweets. And indeed, Stack Overflow is the most popular question and answer website for programmers. It relies on community moderation to bubble up the best answer and weed out unhelpful advice to any programming question. So most of the time, answers come as a code snippet. And that makes it incredibly easy to just copy that code straight into your software and think no more of it. Apparently, as the survey indicates, this is common behavior and part of most developers' workflows nowadays. So as this speaks for the high usability and utility of Stack Overflow, it unfortunately comes with a major risk for application security. So and that's when it comes to security-related questions and usability issues around cryptographic APIs. So this Stack Overflow question, for example, shows one of the biggest issues in Android. How can you accept a certificate during TLS handshake that is not part of the default Android trust store? So this question showed up quite a lot, and we observed that millions of developers have looked it up. So it seems that it's a super important use case for Android developers, but the crypto API just didn't support it. And popular answers on Stack Overflow for this question were unsafe workarounds where the crypto API was simply overridden. They contained this null verifier here, or some kind of variation of it, that renders the TLS handshake vulnerable to man-in-the-middle attacks. So here, certificate verification is simply turned off. However, it technically solved the initial problem, as it now accepts any certificate. And developers seem to be super happy with it. They got rid of their pesky certificate error. And that's probably why they happily upvoted those answers until they became the most popular and accepted answer on Stack Overflow. So in our Oakland paper in 2017, we've shown that those kind of code snippets that were insecure due to crypto misuse were indeed reused in almost 200,000 Android applications available on Google Play. And those included high-profile apps with an install base of over 5 billion users, and apps from security-sensitive categories like business, finance, and health, and social media. Another paper from one of our co-authors demonstrated how to attack apps and steal credentials, credit card numbers, and other private data based on these insecure code snippets from Stack Overflow. In our ICSE paper last year, we've shown that Stack Overflow's content indicators, such as the community-given score and the view counts of given answers, all point towards the wrong direction security-wise, and therefore inadvertently promoted crypto misuse. So usability issues with crypto APIs lead to vulnerable code, which additionally gets promoted and distributed by an Alexa Top 50 website almost all developers use to get help. So to tackle this huge problem, different forms of security advice have been improved, tested, and compared with Stack Overflow. For instance, books and formal documentation, static code analysis tools, and simplified cryptographic APIs that were specifically designed keeping usability in mind. So even though all of these approaches helped in improving code security, developers really struggled with getting running code out of it. They were less productive under given time constraints than developers that were allowed to use Stack Overflow. A very surprising and disappointing example were the simplified cryptographic APIs, as they performed the worst in terms of productivity. Some developers even had to look up the source code of the API to figure out what it actually does. And that's the complete opposite you want to achieve with an interface. They were oversimplified and therefore only supported a very small range of use cases. So the most important thing for us to learn from these studies was that whenever developers encountered a usability issue with one of these approaches, they turned to the web and went for code shopping on Stack Overflow once again. So they went back to their default behavior. So and that goes in line with a famous quote of Richard Thaler, the founder of the nudge theory, which is a concept from behavioral science and economics. So and it says, first, never underestimate the power of inertia. So again, as we've seen, whenever developers encounter usability issues with crypto APIs, they ask Stack Overflow for help. So and the quote continues with, second, that power can be harnessed. So don't even try to change the default behavior, as it's too powerful, but rather try to harness it in a way that it improves the outcome. So and that inspired us for our main idea. So let's try to harness code shopping on Stack Overflow to help developers get cryptography right. Okay, but well, how to do that? So one of our most important findings to answer this question was that on Stack Overflow, similar and secure code examples are available for almost all of the insecure code snippets. So for any insecure code example, there's a pretty high chance to get an alternative code example that practically does the same thing but in a secure way. So in the end, we see getting cryptography right as a decision-making problem. And that's where the nudge theory comes into play. So the basic idea is to nudge people towards better decisions without restricting their options or requiring them to change their incentives. So you rather change the choice architecture to steer people into a particular direction. Here in the example on the right, people have two options for getting upstairs. However, using the stairs is the better option in terms of health. But people prefer to use the escalator. But with the new choice architecture where the stairs now look like a piano keyboard that makes sounds when you walk upstairs, people tend to favor this option. So and that's the key aspect of the nudge theory. It does not try to restrict or require to change incentives. It redesigns the choice architecture in a way that identified behavior leads to better outcomes. So our goal was to design a new choice architecture on Stack Overflow, and it nudges people towards reusing code examples that provide secure and strong cryptography. And it must not interfere with the usability and the utility of Stack Overflow, such that developers can keep their high productivity level using the website and are not drawn away from it. So, but to be able to do that, we first had to find these better alternatives on Stack Overflow. So we had to solve three technical problems. We needed to be able to predict the similarity of crypto API usage patterns, their use cases, and their security, of course. So we combined supervised and unsupervised deep learning to learn these things directly from code available on Stack Overflow. So in the first step, we learned how to predict the similarity of crypto API usage patterns. Thereby, we had to consider a problem that's very specific to Stack Overflow and where deep learning helped. So code examples on Stack Overflow are oftentimes incomplete and erroneous programs. That means their representation, the code graphs, used to determine similarity may be unsound. So you may end up with different code graphs for the same pattern. For instance, if one comes from a complete program and the other one does not. Deep learning, however, doesn't really mind. It learns its own representation that's optimized for the problem it tries to solve. So the network tries its best to determine those features that allow it to predict similarity even though inputs are unsound. So as a first step, we learned a new representation for crypto API usage patterns. And we did that by embedding their code graphs into a vector space using structure-to-vec. So in these embeddings are learned such that similar patterns are closer together, and dissimilar patterns are more far away from each other in the embedding space. So in this way, we can simply use a distance function to determine whether patterns are similar or not. So this is the architecture of our embedding network. It's a Siamese architecture that uses two networks to generate embeddings, either for two similar or dissimilar patterns. So during training, we calculate the distance of both embeddings generated by the network. And if they're too close or too far away from each other, we backpropagate the loss to update and improve the network in generating new embeddings. So in the second step, we wanted to to learn how to predict the use case of a pattern. For instance, initializing a cipher or verifying a certificate. So since we already trained a model for pattern similarity, we considered very beneficial knowledge for predicting use cases. We transferred this knowledge from the similarity domain into the use case domain by applying transfer learning. And in the last step, last and most important step, we trained the security model. And it predicts whether your cipher initialization or certificate verification is secure or not. And here we basically did the same thing again. We applied transfer learning to reuse the similarity information encoded in the embeddings to train a new model for predicting security. So what we did was we just added another hidden layer highlighted in red on top of the embedding network highlighted in blue. So with the blue layer, while the blue layer already encodes the similarity information, the red layer will learn the use case or the security information of patterns. And based on that information, the classification layer on the right will then be able to predict what use case it is and whether it's insecure or not. So we applied different techniques to train the classification network. With one technique called transfer learning, we input the pattern graph into the fixed pre-trained embedding network. Then we only update the weights of the use case or security layer based on the classification laws. With another technique called warm starting, we also updated the weights of the pre-trained embedding network based on the classification laws. So this way, we update the pattern embedding as well in a way that it helps deciding whether a pattern is insecure or not. Okay, so since code similarity does not necessarily need to be learned from code that applies crypto, we were able to compile an arbitrarily large data set. So for instance, theoretically, all public Java repositories on GitHub. However, the data set with the cryptocode snippets we obtained from Stack Overflow was relatively small. So in warm starting and transfer learning helped us in tackling this challenge. Transferring knowledge we obtained from large data sets helped us in learning from small data sets more effectively. So here on the left side, you can now see the results of the similarity model. So it shows all crypto API patterns we extracted from Stack Overflow, highlighted by the use case. So each point relates to a pattern. So for several use cases, you can already see that the similarity model creates dense clusters. For instance, the cipher cluster in blue or the TLS cluster in orange. But it creates sparse clusters for some of the other use cases, for instance, for key generation or IVs. As you can see on the right, the use case model is able to correct this. It moves patterns closer together that belong to the same use case, but that are not necessarily very similar. Here in the middle of this slide, you can see the results of the similarity model again. So the distance still represents similarity, but the color now indicates security. So red is insecure and blue is secure. So in this cipher cluster down here, it nicely indicates that our main idea of nudging people away from insecure to secure is actually technically feasible. So the cipher cluster here has a security boundary. That means that patterns that are close to this boundary actually provide very useful alternatives. They do the same thing, but one is secure and the other one is not. So and this shows a cherry-picked example of it. So on the left side, you see a warning for an insecure pattern as we show it on Stack Overflow. At the bottom, you can see the list of recommendations, which is ordered by similarity and use cases. When you click on the first link, you will end up on the secure Stack Overflow post shown on the right. And as you can see, it is basically the same code. It only differs in the statement that rendered the whole code snippet insecure before. However, developers might ignore basically everything I just showed and copy the insecure code anyway. Whenever we detect an insecure copy attempt on Stack Overflow, we trigger a reminder nudge. And that shows the warning and recommendations again in order to make the user pay attention. All right, so now that we have had everything together, we wanted to test our system design within a developer study. And we had two treatments, the nudge and the control group, and both had to solve two programming tasks, symmetric encryption and certificate verification. We had two metrics, functional correctness, which allowed us to measure the productivity of developers, and security, of course, which told us whether a solution was secure or not. So once again, functional correctness was very important for us, as our nudges must not interfere with a great user experience of Stack Overflow. So developers should be able to happily continue to copy and paste stuff and stay as productive as they have been with original Stack Overflow. And yes, our nudges did not have a significant effect on functional correctness. So both treatments, nudge and control, achieved a very high level of functional correct solutions within the given time constraints. That means it doesn't matter whether you were nudged or not. Stack Overflow remains very effective and efficient in solving programming tasks. So if we now get secure solutions on top, we exactly achieved what the nudge theory had promised us. And indeed, the nudge treatment achieved significantly more secure solutions than the control. And interestingly, being a professional or security knowledge didn't have any effect on security. So solely the nudges made a difference here. So to wrap up the talk, I'd like to show one of the most surprising results of our studies. And that was that it helped tackling null verifiers quite well. So a short reminder, we found out that 91% of apps with code from Stack Overflow contained a null verifier. So certificate verification was basically turned off. Based on those code examples from Stack Overflow, one of our co-authors was able to attack them. Only 0.2% of apps that reuse code from Stack Overflow got certificate verification right. And in another study where participants were only allowed to use simplified cryptographic APIs, none of them got it right. However, nudge participants achieved 77% secure solutions, while the control group was again quite behind with 67% insecure solutions. So that's cool because this was the problem with the highest risk for application security. And it was also the use case on Stack Overflow that had the fewest secure code examples. We found over 1,000 examples of null verifiers and only 50 to 60 examples that provided security best practices. However, if you implement the right choice architecture on Stack Overflow, those few examples seem to be already enough. All right, so what's next? We recently applied for the academic partnership program with Stack Overflow, and that would allow us to further test and improve our approach within a larger field study with real Stack Overflow and real Stack Overflow users. Of course, we'd be happy to test our approach with any company or institution, so feel free to contact us. So we'd love to see Stack Overflow considering some of our ideas. Since almost all developers use this website, we should make sure that they stay on a safe path. We believe that it could have a huge positive effect on how cryptography is used in the real world. All right, thank you very much, and now I'm happy to take questions.
Hi, do you have any plans on trying to integrate this into text editors?
So currently not, but sure, why not?
Given that we have some time, could you go into a little more detail about how these nudges actually appear on the Stack Overflow page?
Yeah, sure.
Oh, okay.
Sorry. Okay, so here, so this is one of the nudges. So here we have the security warning. So the text and the icons is basically inspired by the text and icons used in Chrome for security warnings. So yeah, we show this warning. We show also annotations like below the statement that that causes the snippet to be insecure. And yeah, below the warning, we have the recommendations. So that list displays different Stack Overflow posts, And it's ordered by the similarity of the code to the code snippet you see above in the warning. So that's the first metric we use to order it, and the second one is the use case. So if the similarity is not enough, we use we at least show something that applies to the same use case.
Okay.
And yeah, and then you can just click on one of those, and then we show positive security indicators as shown on the right that indicate that we didn't find anything that causes a problem. And we had another nudge called the default nudge, where we basically reordered the search results on the web page. So if you search for something, we reordered the results based on security, so that you get the posts that are secure first. Okay.
Right, hi. How do you make sure that the results of your user study are not biased? I mean, you're working with developers who know how Stack Overflow looks like, how it operates. So if you introduce something new, why aren't they just following this new feature then?
So we didn't do any priming, like we tried not to mention security or something like that. And we also tested for systematic differences based on the demographics, and we didn't find any.
All right, okay.
So if I'm looking at this example, it seems like it's this sort of this example seems very simple to find. You're looking for just allow all hostname verify. Is this model able to capture more subtle bugs, or is it?
Yeah, sure.
Like, how does it compare to, say, a trivial, we're going to look for these certain indicators and flag them?
Yeah, sure. So this is a very simple example, but we are also able to detect bugs like based on the, for instance, like initializing a key or initializing an IV, or or more sophisticated vulnerabilities. This is just an example, and it shows a very simple case where you basically have to find, like this Java field, that this Java field is somehow applied.
Would this technique also be useful for finding other security but non-cryptographical problems, such as buffer overflow?
Probably yes. I mean, so the whole thing is based on code graphs, program dependency graphs, and we feed these graphs into the neural network. And there are other approaches that kind of use the same representation of code to actually find buffer overflows and so on. So yeah.
All right. Well, let's thank the speaker again. Thanks.
Thank you.
All right. So Shubo from Facebook is going to talk about Crypton frame.
Thank you for giving me the opportunity to present on the behalf of the Crypton team. Crypton is a very young framework. It's essentially a machine learning framework based on secure MPC right now, but hopefully other techniques in the near future. We open sourced last October, so giving us this opportunity to present means a lot to us. I should also say that I'm not a cryptographer. This is only my second time at Real World Crypto, and that might reflect in some of the design decisions we have taken in the framework itself. So a lot of the talk is going to be on how and why we design Crypten the way it is. Every design has a set of trade-offs. Crypten does too. But hopefully a different set of trade-offs than what we have seen in frameworks and libraries in this space, especially in the space of secure computing. I'm going to use secure computing as a very broad term. I don't know if a formal definition exists, but for me it is a computing technique where you're computing on data that is encrypted in some way. To kind of showcase a 40,000-foot view of what these design decisions are, there is a piece of code on the right-hand side which may be foreign to a lot of people here, but if you show this to somebody in the machine learning community, they're going to say, oh, it looks just like PyTorch. And PyTorch is a leading machine learning framework, along with TensorFlow, which also looks fairly similar. And that, in some sense, captures what we are trying to do with Crypten. Our primary goal is to expose the machine learning community to various secure computing techniques and the trade-offs that come with it. There are kind of, in my view, two broad aspects to this. The first aspect is that of the choice of models. In the machine learning community now, for example, let's take an example of computer vision, for example. The models that are prevalent are deep residual networks. They're actually not very convenient to work with in secure computing, mainly because they have these nonlinearities that are hard to approximate. They're also deep in the sense there's a lot of multiplies in sequence that are problematic. So making these trade-offs explicit to the community would hopefully help the community think in different ways, build models that are much friendlier, maybe shallower models. Another concrete example is number encoding. Currently in machine learning, we use float 32. There's a special 16-bit float type called BF16, neither of which are very convenient to work with in cryptography or in secure computing, which likes to work with integers usually. So this is another thing that we want to expose to the community, as there is a space to think about different number encodings when you're training models or doing inference with models. The other aspect is to expose the community to a new feature, a feature that allows them to encrypt data and then do computing with data. And the hope is when you expose this feature, the community is going to think about more applications where the data is sensitive and cannot be trained on in the clear. I should at this point step back and say that Crypten is very much a research framework. Nobody should take this framework and start training on data that actually needs to be secure. We are not at that point yet, but this is our first step. And the hope is, like, when these applications come to be, there are people from this room or from this community can help it build in the necessary security needed for the data that is at hand. So we look at this framework as very much a conversation starter between these two communities because, let's face it, machine learning isn't going away, and privacy is becoming, and security are becoming more and more important. So with that in mind, let's look at what our main design goals are in Crypten. So the first thing, that first major design goal is we wanted to present a machine learning-centric interface based around tensors and computation graphs, which I'm going to get a little bit into more detail later on. That is how machine learning is done these days with neural networks. The second one is explainable performance. By that I mean having a design that is very modular, because modularity helps in figuring out performance. It's easier to work with performance problems in a modular setup than when things are one monolithic piece of code. So this is something we had in mind, because if things are not fast, nobody's going to use it. The third one is debuggability. Crypten's a very young framework, and the field is very new. So we wanted a mode where users who use this can figure out what has gone wrong. So right now we only have a secure MPC setup, for example. So we have a mode where you can have multiple parties on one computer, for example, which helps you debug when models are not training. And I know that debuggability and security are kind of at odds with each other. With security, you are trying to hide stuff, while at debuggability, you are trying to reveal information. And I'm not really sure what the right design call here is. And the last one is interoperability. And by that, I mean, people have been doing machine learning for a while, so there are model formats, models that people have trained, or they have trained or have models specified in other frameworks. We need to be able to import these models and continue training or do inference. So we have a compatibility layer, which is actually open source from Facebook, called Onyx, which is what we use to load models. So not only can we load models from PyTorch, we can load models from other frameworks like TensorFlow, for example, which is from Google. All of these design goals leads to one trade-off, which is the threat model. So we are in the current version of Crypten, we are in the honest but curious mode. And I should also say that this is not something that is set in stone. This is kind of the first setting on the dial. And there's obviously going to be trade-offs between things on the right and the things on the left. So we want to pursue address other threat models as well, but we want to be very deliberate about what these trade-offs are. What do you gain from getting a better threat model, and what do you lose from on the usability side? We want to make these trade-offs very, very explicit. Before I go into the details of Crypten, I wanted to give a brief kind of overview on what machine learning frameworks look like, what their ingredients are, of what we have seen in the last 5 years or so. So what makes an ML framework? So the first component of an ML framework is this object called a tensor, which is really a fancy name for a multidimensional matrix, usually of 6 dimensions and lower. So anybody who has worked with MATLAB, this would be very familiar. So it's in frameworks, the tensors are first-class objects. The next thing you need is something that you need to that will do something with these tensors. So we have different operators that are basically functions that take tensors as input and tensors as produce tensors as output. And these are chained together by directed acyclic graph, which is called a computation graph. You can think of these as operators that are chained together. They take some tensors as input and produce outputs that go to other operators. And this computation graph has special structure, so it usually has one sync node, and then that sync node is used to propagate what is called gradients. So in machine learning, we are trying to optimize a function, so we do a forward pass, and then we do a backward pass through this computation graph for the gradients. I'm going to show you a very, very simple computation graph because a picture is 1,000 words, and it'll help put some diagram behind what I've talked about. So I'm going to start with these square boxes that are tensors that go into an operator, which is a multiply in this case, element-wise multiply of 2 tensors, of 2 matrices. That produces another tensor. So this is kind of what a forward graph is. And to calculate the gradient, we kind of invert the graph. We kind of flip it around, but I'm going to show it as a graph on the right-hand side. So for every operator on the left-hand side, you're going to get a backward operator on the right-hand side. So for the mul, we have a bmul operator, and the black arrows are the gradients flowing back. And then we have 2 special operators, accumulate gradient, which essentially what they do is they accumulate gradients into the tensors from which the input came from. So every machine learning framework in existence has something like this underneath it. Obviously, the graphs get fairly complicated. So let's see what among these components that we have seen exist in Crypten itself. We have tried to be as much 1:1 as possible. So we have what is called a cryptensor object, which is an encrypted tensor, which you can think of it as an abstract base class for people who are coming from the C++ world. It promises some functionality that these tensors will have. It doesn't actually, it's kind of agnostic to what computing you're going to use to ensure security at this point. But right now we use, as I said, a secure multi-party compute. So there is a MPC tensor that sits underneath it. What we want to do going forward is our goal is to have other tensors at this level. So maybe we have a tensor that is backed by homomorphic encryption, for example, at this level as well. Obviously, not every tensor will implement every operation. That might differ between what technique we use. So underneath the MPC tensor, we have two kinds of sharing. So we have an arithmetic shared tensor, and we also have an XOR, a binary shared tensor, and we can go back and forth between the two of these tensors. So what I have said so far is only about interfaces and APIs. There has to be a tensor which actually stores the data. And that is done by this thing called a long tensor. A long tensor is basically a tensor with int64 type. And this is where we kind of cross over from Crypten land into PyTorch land. And this was and PyTorch, as I said, is a leading machine learning framework now in the neural network deep learning space. And this decision we took very, very deliberately. There are a couple of things happen when you have this hard link to an existing machine learning framework. One of the things that happens is the interface filters up. So whatever functionality and the API the long tensor has, it filters up the API all the way up to the crypt tensor. You may or may not choose to implement all of these APIs, but it does filter up, and that gives a very natural interface to the people in the machine learning community. The other thing that happens is performance gets linked in the sense when things in PyTorch gets fast, Crypten gets fast, and that's also a very deliberate choice. And the other thing also happens. For example, nobody had, well, there really wasn't no long tensor in PyTorch before Crypten showed up. So Crypten also influences PyTorch design. So there's a nice give and take going on between these two frameworks. And the third one, maybe a little bit non-obvious, is the communication library. So machine learning is a very distributed operation. Currently, we can train models on thousands of processors, so there's a communication library that does this. It turns out that a lot of the communication patterns that we see in multi-party compute map very well to the communication libraries that we use for distributed machine learning. So this was a very lucky find in some sense. What this design choice also leads to is it kind of decouples where protocol-specific optimizations need to happen and where non-protocol-specific optimizations need to happen. So anything in the protocol-specific stuff can happen in the Crypten layer above the dotted line, and then anything that is not to do with the protocol, for example, making the communication libraries fast or making some math operations fast, can happen completely in the PyTorch layer. So this makes life a lot easier, because then we can make minimal code changes to Crypten or PyTorch depending on what we are doing. So now that we have seen tensors, let's look at what operations does machine learning training needs. And this is obviously a restricted set of operations than what you would do in a general purpose program, but there are quite a few challenges. So I'll go from the simplest to the hardest. So the simplest from the view of secure MPC. So the two simplest ones are matrix multiply or a dense matrix multiply, which is it's essentially is the component behind a fully connected layer. A fully connected layer is essentially a matrix multiply followed by adding a vector called a bias. And this is easy to do because it's all additions and multiplies. Additions come for free. In additive sharing, multiplies come with Beaver triples. And convolution, the way it's done in machine learning, is usually done using matrix multiply because the spatial extent of this convolution filters is very, very small. So if you can do matrix multiply fast, we can do convolutions fast as well. And the Beaver triple formula doesn't not only holds for scalars, it holds for tensors as well. So you can do it with tensors. The next up is logs and exponentials. So logs, these are all done through various series approximations. So logs we do through householder iteration. Exponential we do a variant of repeated squaring. We do division using Newton-Raphson. Then we do power, power and square root using essentially exponential for power and log for square root. And then finally, we have operations that are very hard to polynomially approximate. So we have ReLU, which is it's a weird sounding function, but all it does is if a value is negative, it sets it to 0. And if a value is positive, it just lets the value through. So you can think of it as an if condition, basically. People have tried doing polynomial approximations of this, but it never actually works. So these are the last line of ReLU and max and argmax are done using circuits. And this is where we have to go from arithmetic sharing to binary sharing and back. And max is usually used in layers called, there's a max pooling layer, which essentially looks at a filter and finds the maximum value within the filter. And argmax is also used in the same layer. So now that we have seen both the tensors and the operators, we need something above Crypten to make things work. And the stuff that we need above Crypten is to essentially some metadata and data to accumulate gradients. So we have a separate tensor, which is called an autograd cryptensor, which is used in the backward graph. So we have these tensors separate, but it's quite likely we are going to fuse these tensors into one tensor, which we can use for both the forward and the backward graph. And we need one more object called a module. Module is essentially a kind of a convenience object. So in the computation graph, you saw these operators as nodes. So it turns out that it's good to have some state along with these operators, and it's good to have a consistent interface for this operator. So there's a forward function and a backward function. So what the module does is takes all these operators and adds this kind of a standard API so that this graph can be traversed very easily. A module can also contain other modules. So you can take a subgraph and express it as a module. So there are some layers of the neural network that are better expressed as subgraphs. So that's where the module comes in handy as well. What this module allows us to do is to essentially use what I said, ONNX. So it gives us compatibility to other models that have been written out using PyTorch or TensorFlow or any other framework. And then we can read it through ONNX as a sequence of modules, essentially. What this allows us to do is if you have pre-trained models that have been trained non-encrypted, but you want to do inference on encrypted data, you can use those pre-trained models. You don't have to retrain anything. If you have models that are specified in a PyTorch-like fashion, you can use ONNX to read this non-trained model, and you can train it from scratch also using Crypten. So we've kind of seen all of the components major components that Crypten has. I'm going to spend a little bit of time on communication as well in the next slide. This term might not mean anything to most people here. So all reduce is a communication pattern where you have a bunch of parties or peers who have a value, and they need to exchange these values with each other, sum all their values, and then broadcast it back to everybody. So this is essentially open to all in MPC speak. And already, so on everything that I'm shown on the left is something that already exists for distributed machine learning. Distributed machine learning needs this communication operators as well. The next part is reduce, which is the same thing where you don't do the broadcast back. So you send data to one party, that party sums up all the data, and you reduce to that party. And that's open to one. You can also do a broadcast. One party can send different values to different parties. So this you can think of as communicating from trusted dealer to multiple parties. So these communication patterns already exist for doing distributed machine learning. I also realized that this is constrained because this is fine when you have n out of n shares, n parties, and n shares. It won't work for any kind of threshold scheme. But it turns out that another form of distributed machine learning, which is called model parallelism, needs more flexible communication libraries. And those communication patterns used for model parallelism are also can be used for doing more flexible communication that are needed in threshold sharing, for example. So those are coming as well. One thing I should also say is these communication patterns have been around at least in computer science for a long time. They actually come from this very old communication library called MPI. I don't know if people have used MPI here, message passing interface. It's used in scientific computing a whole lot, because in scientific computing you have a bunch of compute going on in parallel, and then you need to broadcast results every once in a while. So we found that quite interesting, that it looks very much MPC-ish from that perspective. So I wanted to give some examples of code. I've shown one example at the very beginning, but I wanted to show how similar code in Crypten looks like to code in PyTorch. So I'm going to start with some code on the left in PyTorch. These are very small examples. So this is something that takes two tensors and adds them. And the code on the right is Crypten doing the same thing. There's not a lot of difference. You import a new library, and everything has a crypt in front of it in some sense, and then you do have some init. So this makes it very intuitive for somebody who had used not just PyTorch, even TensorFlow looks very similar to this. If you want to do gradients, so here's some code on the left and right, which does gradients. So on the left, we have a tensor. There's a cross entropy is what is called a loss function. On the right, we have the same variant of code in Crypten. It looks very similar. And what we have done also is we have machinery in place to run Crypten completely in a browser. So a Jupyter Notebook is a very common tool in the space. So we can load up, for example, Crypten in a Jupyter Notebook to kind of get started very easily. And this has proved very, very beneficial for people who are starting on this, starting to kind of play around with this. And in fact, all our examples in our source code is actually, they have examples in Jupyter as well, so people can get a taste. I also wanted to show you what loading a real model and a real data set looks like. And this is a very small inference example with ImageNet, which is a very popular data set in computer vision, for example. So on the right, I'm going to show you code. So what I'm doing is here is importing some library, initializing Crypten. Then I'm initializing an image transform, which crops the image, for example. I load the data set, which is it's loading it from a folder, ImageNet folder. This is a data set about 1.7 million images or so. And then I load a pre-trained model. A ResNet 18 is a full-scale model. It's not a toy model. And then we encrypt the model, we encrypt the image, we get an encrypted output, and you can reveal the encrypted output, and you're going to get the same result as you would have done everything in plain text. So it doesn't look all that different from what you would do if you were not encrypting things. So this is what we have now. So where do we go from here? And by we, I mean not just people at Facebook. We would love to have participation from both people here and in the machine learning community as well, because this is a long road. So the first thing on our mind is improving performance. We work in, as I said, an int64 space. There's very little optimized libraries in int64 space. So we are writing some of like a more optimized version of int64 matrix multiply, int64 convolutions. Facebook has a library called FBGem for matrix multiply, so we're writing vectorized code, usually using AVX512 for faster matrix multiplies. We aren't done yet, so we have done some initial implementation. We have to do more here. On the hardware side, my wish list would be support for wider data types. 128 would be fantastic. Wider vector SIMD lengths would also be fantastic in this space. The next one that we are working on is a trusted third party. So our current trusted third party is a trusted dealer, which I think is fine as a first cut, but we want to explore other options of generating Beaver triples. One idea may be using something like an Intel SGX or other homomorphic encryption schemes in the space. Though I sometimes wonder why we don't have a service for generating Beaver triples that'll make our life a whole lot easier. These are some of the near-term things that we're working on. Going forward, longer term would be support for other secure computing techniques, as I alluded to. Should we have homomorphic encryption-based tensors? Should we have some sort of enclave-based tensors? We don't have the right answer, and we don't know what people would like to use. So in some sense, we are looking for feedback as well. And also, other research-like things. For example, privacy and security are not the same thing in many ways. You can do secure computing, but at some point you have to open the result to actually take an action. So you want, maybe your model and data is encrypted, but at the end of the day, you want to know what the classifier told you. And that might leak information about the model and the data. So how can you quantify how much information you're leaking? And this goes to like maybe marrying things like differential privacy techniques when we open from a secure computing domain, and how much noise to add is one research direction that we want to pursue. But one thing that we want to keep in mind is no matter what we do as a community in this space, we should work in models and data sets that are actually practical. There's a lot of research that works in the space using, say, MNIST, which is a very small data set, or CFAR10, which is also a very small data set. These are not very useful. They're useful in proof of concept, but it's very hard to take something that works in, just say, MNIST and CFAR and then extrapolate it to something that is really practical today. So with that in mind, I want to set forth a challenge of some sort for everybody here and also in machine learning in some sense, but a little bit of history. So machine learning has had this challenge called the ILS-VRC challenge. I think it has run since 2010, I believe. I don't think it runs anymore. So what this challenge set about was, first it created a large data set of 1 million images. Each image came with a tag of what object was there in the image. And the idea was to train a model on the image and then classify with high, and on a test set, classify with very high accuracy. So this is solved in some sense. We can do this with very, very high accuracy. And not only that, we can train a model on a 1.7 million image data set in minutes. I think the record is 2 minutes, 43 seconds or so, but with some degradation in accuracy, but within 15 minutes we can train very, very good models. And this has completely changed machine learning as we know it in the last 5 years. In some sense, the popularity of neural networks now is because neural networks were shown to be the best way of doing this. So in the same vein, I have a question. So say we want to train on 1 million encrypted images, say from ImageNet, classify with high accuracy. We can cut ourselves some slack. Obviously, we are working in an encrypted domain. We are not going to get everything we want. So maybe we want an accuracy of, say, a relative 20% of what we can do now in clear text. And then instead of being done in a minute, say we give ourselves a week. I don't think anybody has done it, to my knowledge. But if we can do it, I think this will be a step function change in the community. It'll be the same step function change as how neural networks were first able to do the ILS-VRC challenge, I believe, in 2012. With I forget the number, but it was a massive increase in accuracy. It'll be that kind of a change. So with that, I wanted to introduce you to the Crypten team at Facebook. We are a very, very small team. Alphabetically, we are Auni, Brian, Lawrence, Mark, Shobha, myself, Vinny, and Xing. But we are very open to collaboration. We are a research group, and everything we do is in open source. So we would love for people here to be interested in what we do and collaborate with us. Thank you.
So in the examples that you showed, I didn't understand you can actually specify a multi-party machine learning situation. Like, if you want to train a model using data from multiple parties, how do you declare the parties?
Yeah, so what I didn't show you is the tensor constructor that you saw has a source argument. So I'm basically showing one party here. So you can have one party have the data and another party have the model, and you specify the sources. So MPI has this notion of a rank. So you can say if rank equals 0, which is the first party, then you have the data. If rank equals 1, you have the model. And we can do multi-party compute in any number of parties. Yeah. So we have it in the examples, but for convenience, I didn't show it here. Thanks.
Hi. Thanks for a nice talk. So when you spoke about the performance coupling between sort of PyTorch in the lower layer and then the Crypten at the upper layer, you spoke about it very positively. But it can also have a negative side to it, because I assume the developers of PyTorch are interested in optimizing PyTorch for the regular case, and that sometimes might make it slower for MPC. Like if they reduce the amount of operations greatly, but at the cost of increasing the amount of multiplications, say, right? That would be faster in a regular execution sense, but an MPC will be slower. So do you have any thoughts on that?
Yeah, I mean, that's a good point, and that, I think, battle will exist. Just the fact that I know the PyTorch team very well, so it's easy for us to influence, let's say, those decisions. And for example, being able to do, convolution in the Int64 space. If you went to PyTorch team and said, I want to do convolutions in the Int64 space, be like, you're crazy. But here we are. But yeah, we are very cognizant of this, and we are trying to push to have more of these features in PyTorch. So the community in PyTorch is huge. So the motivation there is if we can do these changes in PyTorch core, then everybody benefits in some sense. But yeah, absolutely, that will exist always.
Thanks.
You mentioned that you have to do some transformations potentially to do like the max type of operator. Do you implement specializations for a particular number of parties, such as those in like APY3 or SecureNN? Okay.
No. That was an explicit design goal, not to have party-specific optimizations. And I don't know how far we can go with that. At some point, we may have to have party-specific optimizations, but we wanted to have as any number of parties. And that was actually a problem for us. I think our first implementation, we were using 2 parties, and then we went to 3, and everything broke.
Hello, Sahar Mazloum from George Mason University. Thank you for a great talk. I really enjoyed it. So my question is about, so the framework that you just described is another framework that how to do machine learning in secret computation. And so as we saw yesterday, there are a couple of other frameworks out there that does similar functionality, provide similar functionalities. Do you have a kind of do you have any idea of how your functionalities compare to others in terms of, because everything goes down to how you approximate those functions, like for example, log that you just mentioned, or max pooling, or some other functionalities. So do you know, do you have a benchmark in mind that how do you compare with others, how the approximations differs in terms of the performance, the leakage that you just touched base on, and some other features?
Yeah, so our max is actually not approximator. Max is done using a circuit, so it's exact max. Actually, we are doing this now for our own sake. The approximations we do are valid in number ranges that we see in training. So we want to do it. I should also say the frameworks that were discussed yesterday, they're much more general frameworks. You can write a code in that specific framework with particular annotations. Obviously, we are not doing that. Everything we do is very, very specific to machine learning. And this is a decision that we took very, very consciously. So our goal was to avoid compiling as much as possible, because what we have seen is Languages take a long time to get traction in a community. Just going from Python 2 to Python 3 took 10 years, and that's just one language. So we wanted to stick to an interface that is familiar to community and start from there. But yeah, we are starting to look at comparing with how good our approximations are, how fast they are. Actually, our slowest operation is a division operator, which is kind of weird. The Newton-Raphson. So the other thing with like using Newton-Raphson is you cannot in a secure space, you cannot say, when did I converge? Because that reveals information. So we have like a fixed number of steps of Newton-Raphson that we do. And that works for some number ranges, but we have to see what we can do for others. It's tricky.
I feel what you say. I implemented that. Thank you so much.
So in your talk about the N64 for deep learning, your dynamic range, is there a decimal point floating over to the left somewhere? Because otherwise...
It's fixed point right now, which is represented as an N64, essentially.
So log is the lookup in a table of 64 numbers.
Log is not a lookup. We actually do a series approximation for log. So log you can expand as a series, right?
Right, but that's not, if you're taking a log and you're rounding it down to integer or an N64, it's the map, there's very few outputs.
There are what?
There are very few outputs.
As in the precision or?
The biggest log you can have is 64.
Yeah.
And then the smallest log you can have is 0.
Yeah.
And so why do we need a Newton-Raphson iteration for this?
So you want because the N64, basically it's a fixed point representation in N64. So it's a decimal point that is fixed.
Oh, over in the left somewhere.
Yeah,
okay,
yeah.
All
exactly,
right.
yes.
All right. Let's thank Shuwo again. Next speaker, Flavio. Oh, there.
This one? You just hit regular. There you go. I need this one.
Speaker is Flavio from IBM Research.
Thank you. Good afternoon, everyone. This talk is towards a homomorphic machine learning big data pipeline for the financial services sector. So everybody's talking about machine learning today, and I'm glad a lot of people talked before me, so I can cut a lot of the parts that I was going to say. This talk is about a collaboration that we did with one of the banks, with Banco Bradesco in Brazil, in the first and the second quarter of last year. I would like to thank my co-authors in this work, and also my collaborators, Shai and Victor, that were with us there, and also the reviewers of this conference, because since I couldn't reveal the name of the institution until today, it was kind of a very dry abstract that I had to submit. But hopefully I'm going to be able to present a lot more today. So just to put things in context, Banco Bradesco in Brazil, Latin America, not everybody heard of it, but it's the second largest private bank in Brazil. It's, in terms of brand, it's the most valuable brand in the country, and this is important because if you consider data leaks, data exfiltration, and all sorts of things that can happen that damage your brand. So security is paramount for them. The number of clients, individual current account holders, is 72 million. They do 70,000 tasks. This is not only the transaction, this is the task that involved the transaction, the commits on the database, and everything else that happens on the back end per second. And you're going to say, well, why they are looking at homomorphic something to protect the data is because they embrace advanced technology very early. So they want to be ready for when technology is available. So what was the challenge that they came to us is sharing data amongst the different business units. It's an interesting thing because there are, particularly in regulated industries like financial services, because there are not only privacy laws, but antitrust and a lot of other things that don't allow people to see data from different departments of your own company altogether, right? So they can be breaking some regulation somehow. The order is, this year, the equivalent of GDPR starts to be enforced in Brazil. So they wanted to be prepared to how they're going to move this forward, which then led to, at the end of 2017, beginning of, and discussions in 2018, for them to start looking at what sort of technologies could be applied to keep the data encrypted all the time. So they approached us because of homomorphic encryption. And the other important challenge is how do we do this in a hybrid cloud environment, right? And there is a lot in there. So when you do this sort of work, what are the people that you're going to get together, right? So just to give an example of the kind of the breadth that we had to discuss there, we had our sponsors in their team, which were their R&D team and the CTO. But then you need the systems infrastructure people involved because you need to understand what the impact of this new technology is going to cause on everything else that people have there. You need the data governance people because you need to show that what you are doing is secure to some extent. The security people are going to say, well, what the security people are doing there? Well, homomorphic encryption and some of the advanced crypto stuff that we talk here is not mainstream yet. And these people don't understand necessarily what it is. So there was a whole education process to show them what security can be achieved with it. And the important people, the data analysts, because they are the ones that are going to consume whatever we did. And obviously, our team, with very frequent technical meetings and exchange along the process. So, just to put things in context, homomorphic encryption allows us to process data without giving access to it. Technically achieved by computing unencrypted data without ever decrypting the data, which basically means that it's not encrypted in the registers or anything of the machine. It addresses that problem that I mentioned before, which is how I can share data when data can only be shared on a need-to-know basis, and there are regulations and so on. So how can we address that aspect? And it's important to consider what threat model we are addressing here for this scenario. It's the honest but curious, which basically means that the entity performing your computation is a legitimate entity to perform that computation, but it wants to learn from what you're doing. And FHE is based on lattice cryptography, therefore quantum resistant to the best of our knowledge today. So let's have a look at the problem. Banks and financial institutions use machine learning, something what people call traditional machine learning, which is basically regression-based machine learning, for a variety of things. And you're going to say, well, why not the fancy neural network stuff? Because they are regulated industries. You need to be able to explain easily why a given prediction was done in a given way. So if you have many hidden layers there and you can't say why a decision was taken, that can be tricky. So banks use this a lot for certain tasks like marketing, loans approval, and so on. So the data set that we used comprises real financial data over a window, is a sliding window of 24 months of measurements that they make about every one of us. So basically the bank measured me in 546 individual explanatory features, which is a mix of quantitative, categorical, and binary features. And the other important thing is the amplitude of the values. Take just one thing. Let's say your current balance. Your current balance might be minus a few $100 or plus a few $1 million, right? So when you're trying to do machine learning, this type of things, things get tricky because of how you do, how you manipulate the precision you want to do. So this is what they do, right? And with that group that we put together, we had to figure out what the use case and what we're going to do. So we looked at, OK, so let's put a fully homomorphic encryption transaction data store and see if we can do predictions, if we can do machine learning with that. So we took the marketing scenario. The marketing scenario that they work with is one that can they predict whether someone who is going to need a loan within the next 3 months. This is an important task they do because they can upsell loans. But look at the second bullet there. It's a rare event in that data set. It's around 1%. Which basically means that if I didn't do any machine learning, just said no, I'm going to be right 99% of the time. But the golden nugget is in that 1%. If you can find that 1% in your transactions, that's where you make money. So that's why the importance for this. And the data is very sparse. So what was the success criteria for us to do prediction homomorphically? The first one was, if I have an existing model and existing data, can I encrypt the model and the data, run the predictions with the same accuracy as the predictions done without encryption, right? And this is an important aspect because you don't go to a bank and say, well, you know, this 10 years of modeling that you have, throw it all away because we're going to start all again. No, so you have to be able to do that with what they have. The second is to perform a task in machine learning, which is very important and quite often overlooked, which is variable selection, right? So remember, I said 546 explanatory features, but the models will have tens of features, because although we have a lot of features, many of those features are highly correlated. So you have to get rid of those features and find the ones that are the most relevant for the condition that you try to predict. And the question is, can we do this variable selection homomorphically with the same accuracy that's done without encryption? And so those were the two main success criteria. And obviously, with some acceptable overhead, because if you're doing everything as we saw from the last talk, things can happen in seconds or a week or so. So how do they do it today? And this is an important aspect, is everything is done on premise, because this data is private, it's confidential, it's sensitive, so they don't put this information in the cloud. And to prevent exfiltration of data, the environment where the data analysts work is a secure environment. So you can't take your cell phone, that sort of stuff in there, right? So, and you can't take your laptop and come back with the data either. So the data and the machines stay where they are, which is very costly for organizations to do it that way. And some of the organizations, because of the regulations, the data has to be physically separated, and you can't even use multi-tenant environment systems, right? So you can see that the cost of infrastructure, if you have to do this in-house, is very high. So we came along and said, okay, let's do this in the cloud, right? So if we own the premises, which is secure, we take our transactions, we encrypt our transactions, and we send them encrypted to somewhere in the cloud where we can do predictions if I've already got a model, or I can run some machine learning to derive new models. I have encrypted predictions, so the cloud cannot see anything. It's honest environment, but curious. And I bring back the results, and then I can decrypt. So that was the premise that we did. So, and we did that, right? Our paper shows all the maths and how we organize the data, how we encode the data, how we try to optimize everything for a SIMD-like computation. But what I want to show you is more of the results that we got. So our experimental platform, a mainframe. And you're going to say, well, mainframe, why a mainframe, right? So why can't you do this elsewhere? Because most of the transaction data is on the mainframe out of the financial institutions. They are also currently evaluating how they use the mainframe as integral part of a hybrid cloud strategy. So you have the elastic environments that you can consume in the cloud and how this can work there. Our library, HLib, runs in the cloud, runs both in the cloud and on the mainframe. And it's open source. So these were some of the characteristics that were appealing to them to come to us and talk, and the requirement of the mainframe. So results, how does this look like? Prediction. We took an existing model. This is a 16 variables existing model. We took the data, we encrypted data, we encrypted the model. We run through an encrypted logistic regression-based prediction model. And the accuracy was pretty good, right? Because we are using here an approximate number scheme for homomorphic encryption, and the accuracy was very good. So that part number one. So when we proved that we could do predictions with the same accuracy, the next step was, well, can we do variable selection? Can we do the training? Can we retrain that model with new data, but now encrypted? And we did this too. So what we're showing here is the log loss of the variable selection based on how many steps we do in the training versus the sigmoid approximation that we used, right? So that was mentioned before, because you cannot stopping you cannot check how good you are, and you cannot stop your computation. You have just to. So we did that, and we showed that for 5 and 6 steps with sigmoid approximation of 3rd degree or 7th degree was pretty much the same when compared to this yellow curve is doing it in the clear without encryption. The next question you're going to ask me is, well, how long does it take? So this is the computation overhead. Computation overhead in terms of, depending on the security level, for 256-bit security was 50 times. And you're going to say, oh, dear, it takes 50 times longer to compute. No, this is pretty good when you're talking homomorphic encryption, right? In 2018, would be a few hundred times. The memory overhead for the prediction wasn't bad either. It's about 20 times for 256-bit security. So once we have this, how do we put this together, right? Remember this? What's wrong with this chart? What's wrong with this chart is that this is the kind of a more research academic way of looking at it, where I have a machine learning thing and I have encryption and so on, but I'm missing this part, which is how do I deploy? How do I generate my keys? How do I store my keys? How I manage my keys? How I make sure that the whole system works and there is the coordination that I require, right? Which basically means that I still need the secure environment because on that side, I have data in the clear, become encrypted to be deployed in an unsecure environment. I have to retrieve my keys from my key store. And remember, these are homomorphic keys. They are very, very large compared to everything else that we have been using so far. And when I decrypt, I need my secret key to decrypt. So again, I need a trusted environment, otherwise I can leak my secret key and then everything is gone away. Right, so this is the environment that we have been working recently and how we integrate everything in a framework that can actually be consumed for whether you do machine learning, whether you do searches, or some of the others. Okay? And I have 1 minute for questions.
Do you see homomorphic encryption as a way of reducing consumers' exposure to like maybe data leaks and stuff?
Well, data leaks is still going to happen, but if it happens in an encrypted form with a strong encryption, then there is no damage on the data being leaked. A lot of the data has already been leaked just by going on the internet. And it has been captured in an encrypted form, but people are trying to decrypt it. So if we get quantum computer somewhere, or someday that could be vulnerable. With lattice-based encryption, then it's less so.
Last question.
Yeah, I would be curious to know, based on your experience and all the work that you guys have done, how far away do you think we are from, fully homomorphic encryption to be at a point where it is sort of feasible for most of us to be able to use it, sort of in a commercial setting, or a lot more than what we are able to do now, which is not much because of the performance costs associated with it?
Well, actually, it's very use case dependent, and we tend to say that right now we are at that inflection point where the performance is adequate for certain use cases. most of what I showed you runs as a batch system. The predictions, they are not sub-second predictions. It's an overnight task. So if it takes an hour or 10 hours to run, but with security, and I can outsource that to the cloud instead of having to do everything in-house, that makes a lot of sense.
Thank you.
Great. Let's thank the speaker again.
Thank you.
It's breaks now.